Hello and welcome back to Abstract Linear Algebra, the video series where we talk about linear algebra from a general viewpoint. This means that we consider general linear maps which we could represent by matrices. And indeed, in today's part 32, I will show you how we can use that to solve general linear equations. This means this video gives an example to the general discussion we had in the last video. However, as always, before we go into the details, I first want to thank all the nice people who support the channel on Steady, here on YouTube or via other means. And please don't forget, as a member of this channel, you can download additional material for all the videos. For example, you find quizzes, PDF versions and books for linear algebra with the link in the description. Okay, then I would say let's immediately start by considering a general linear map we call L. And as always, it should act between two general vector spaces V and W. And then in the case that we have finite dimensional vector spaces, you also know that the rank nullity theorem holds for L. This one tells you that the dimension of the range of L plus the dimension of the kernel of L is always equal to the dimension of the space we put in. Hence you can use this information when you want to solve a system of linear equations. And in this abstract formulation with a linear map L, the system of linear equations is just given as Lx is equal to b. And now, as we have already learned in the last video, we have at least one solution if b lies in the range of L, and the kernel of L tells us about the uniqueness of this solution. Okay, so now I think we are ready to make everything more concrete, so let's look at an example. And as often, we will just take polynomial spaces for our vector spaces V and W. So let's take the four-dimensional space P3 of R. And as you know, we have a simple basis on this space, which we call the monomial basis. So as often, we can just call this basis B, and here you should see that we start with the monomial M3 and then we go to the constant M0. And the definition of the monomials is always the same. We have an index k, where k stands for the power of our variable x. And now our example for the linear map L should be given by the derivative operator. So p is sent to p prime. And of course we know what this means for the monomials, because they get just reduced with the index and the factor k comes in front. The only exception for this nice formula we have for the M0 monomial, which is sent to 0 because it's just a constant. This means here on the right hand side we have the 0 vector in the polynomial space, which is the polynomial which sends every x to 0. In fact, this example we have already discussed in part 25, so the matrix representation with respect to B should not be a problem here. And here please don't forget, we have the same vector space and the same basis on the right and on the left hand side, so the matrix representation should be given by a square matrix. And now let's use what the map L does to the monomials, so we know that M3 is sent to 3 times M2, so we actually have a 0 in the first component and then a 3 in the second row. And the other entries in the first column have to be 0 as well. And with the same reasoning with M2, we get a 2 in the third component in the second column. And then finally we can just use that the derivative of x is just the constant 1. And moreover, M0 is sent to the 0 vector, so we need a whole 0 column in the end. Okay, so there we have it. This is the matrix representation of our linear map L with respect to the basis B. And since this matrix is not so complicated, we can immediately read the kernel and the range of this matrix. In fact, the kernel has to be one-dimensional because this matrix is almost in a row echelon form. So we see we have exactly 3 pivots, but only one free variable. Therefore, our kernel can be spanned by a single vector in R4. And indeed, this one can be chosen as 0, 0, 0, 1. And that's it, that's our one-dimensional kernel. And in conclusion, we also already know that the range of our matrix representation has to be three-dimensional. And indeed, by definition, it's always spanned by the columns of the matrix. Hence, the first three columns already give us the whole range of the matrix. So this is really nice, but as you know, we are not interested in this matrix representation, but rather in the abstract linear map given by L. This means we have to transform these vector spaces in R4 back to our original general vector spaces V and W. And you know, this is quite simple because we only need our basis isomorphisms. And there, please recall, usually we denote this basis isomorphism with respect to a basis B by phi with index B. And indeed, phi B sends the general vector space V to R4. So this one we know, and it's not so complicated. And in fact, in this case, we have exactly the same thing on the right-hand side, just for the vector space W. And now please note, our abstract linear map acts on the upper level, while our matrix representation acts on the lower level. Hence, with that picture, we can write the relation between L and the matrix representation. Namely, first our basis isomorphism acts, then our matrix acts, and finally we have the basis isomorphism in the inverse. So there you see, this is exactly what we have in the picture for the acting of the linear map L. And now this nice formula we can just use to transform the kernel and the range. In other words, now we want to have the subspace in V, which is given as the kernel of L. In other words, we just have to know how the kernel changes when linear maps act on it. In fact, you might remember that in former videos we have already discussed how the kernel changes when we have three ingredients inside like that. In fact, these two parts here have to be invertible, and then only the right-hand side matters. Namely, you can remember that this right-hand side here comes with the inverse to the front. And then inside we only have the linear map, which is given by the matrix representation. And there I can tell you, it's always a good exercise to use the definition of the kernel to check that these two things are exactly the same. And moreover, a similar thing we also have for the range. In fact, also this formula for the range we have already discussed in former videos. So what we have here with the combination of the three linear maps where the left-hand side and the right-hand side are invertible is simply that the first part here comes to the front. However, there we don't put an inverse to it, it remains like it is. Also, this nice formula you can easily check by using the definition of the range. Okay, so now both formulas tell us in order to get our abstract subspaces, we just have to transform the two spans from before. So let's start with the kernel, and there we only have the question, what does this vector in R4 represent in V? And our basis isomorphism tells us that this one is M0. In other words, all constants in the polynomial space give us the kernel of L. Very well, and now we can do exactly the same thing with the range of L. There we have to transform three vectors, but we also see it's not hard at all, because it's simply M2, M1 and M0. To be fair, we actually have constants in front of the vectors, but they don't change the span at all. Hence we can simply write the range of L is given by the span of M2, M1 and M0. And again, you can check that the rank nullity theorem is satisfied, so the dimensions of the two spaces fit together. So maybe after all this work, we can finally discuss a linear equation for this operator L. So the formulation would be, when do we have L of P is equal to another polynomial G? And since our map L is given by differentiation, this equation asks about antiderivatives for the polynomial G. And there I can tell you, another name for antiderivative is given by primitive. However, since this is a linear equation, we already know how the general solution set looks like. The solution set S is either empty or given by an affine subspace in V. And in the second case, we just need a particular solution which we could call P tilde. This means here P tilde prime is equal to G. This means if we find one antiderivative of G, then we immediately have infinitely many. However, we also see that the difference between two antiderivatives is always a constant. Indeed, the kernel is just one-dimensional and spanned by all the constants. This one is an important result from analysis, but now we have proven it in a linear algebra setting. Okay, so this is all I want to tell you about this particular example, and I would say we can continue our discussion about general linear maps with the next videos. In fact, there I want to start with the topics determinants and eigenvalues for linear maps. So I really hope I meet you there again, and have a nice day. Bye bye.